Hey guys, we're going to take a look at the momentum conservation notes. Your notes starts with this document right here, and you'll notice that there are two vehicles, a truck and a car, both moving, and it gives you the speed of each vehicle. This is before the vehicles collide, and this image over here is after the vehicles collide. So we're analyzing this interaction between the vehicles. In your chart here, you are going to list the mass of each vehicle, so to be 500 kilograms, 400 kilograms for the car over here. Velocity initial before is 5, and velocity for the car before is 2. So let's see, it'll be 500 times 5 is 2,500 kilograms meters per second for the initial momentum, and then on this side it's 400 times 2, so 800 kilograms meters per second. Then after the collision we use these values for the truck and the car, and then when you add up the momentum before, so you have to add this first value plus this value over here, that will give you the answer to this question right here. Then you add the momentum after, that gives you the answer to this question. And what happens is the two numbers wind up being the same. And this is an important relationship in our next topic, which discusses the momentum before an interaction and how it's equal to the momentum after the interaction. Okay, you don't really need to come up with these two equations right now because we're going to talk about it in the PowerPoint right now. So we're moving on to page 2 of your notes. All right, so the law of conservation of momentum. It means that the total momentum of all objects interacting with one another before and after an interaction is equal. They are the same. So it doesn't just have to be two objects that are colliding, it could be multiple objects. So when we were talking about the impulse momentum theorem, we were only dealing with one object. We only analyzed the change in momentum of one object. Now we're going to be dealing with multiple objects. So this is the law of conservation of momentum. It states that the initial momentum is equal to the final momentum. So notice this is the momentum of object 1, this is the momentum of object 2. Both have an I for initial velocities. Then this is the final momentum of object 1, final momentum of object 2. Something that I have been doing recently when I teach this topic is above this first quantity, I put P1, above the second one, P2, and over here, P1, and over here, P2. And for some reason, that just seems to help a lot of students in organizing the values. So you just have to remember to always put initial on the left, final on the right when it comes to the velocities. So now we're going to talk about the various types of interactions that could occur when objects either collide or push away from each other. Our first scenario is recoil or an explosion. And this is when objects start together, such as a cannonball in a cannon, and then an explosion occurs and they recoil away from each other. So the cannonball goes in one direction while the cannon itself recoils backwards a little bit. You'll notice the same thing with gunfire. Both objects will move at the same speed initially. Many times they start at rest. So our cannonball and the cannon, they're both at rest before the interaction actually occurs. So VI0. So this is just a fun little video of a rocket cart moving along. Let's just fast forward a little bit. So you'll notice some exhaust coming out the back here. And the whole reason that that works is because of recoil. So anytime a fire extinguisher goes off, you may have seen people sitting like in a rolly chair using a fire extinguisher or on a skateboard, and it makes them go backwards. And that's because the exhaust is pushing in one direction while the object that's on wheels goes in the opposite direction. This one's one of my favorites, the spud gun. So potato gun.
Oh, this is gonna be funny. Is it going cannon?
So you can't miss the recoil there. Okay. Our next type of interaction is perfectly inelastic collisions. This is when objects collide and stick together, so they'll have the same final speed. When a baseball catcher catches a baseball, the ball and the glove will move at the same speed. When a goalie catches a hockey puck or a soccer ball, they will move at the same speed. If a bullet is shot into a block of wood, the bullet and the block of wood will move at the same speed after the collision. In these scenarios, kinetic energy is not conserved. So if you remember when we were talking about roller coasters and we said, oh, energy is conserved, here, kinetic energy is not conserved, and that's because the object actually becomes deformed during the collision. And that energy is transformed into other non-mechanical forms of energy like sound, heat, light, etc. So here are a couple examples of perfectly inelastic collisions. So they stick together and move at the same final speed. Again, the same final speed. Our next type of collision is inelastic. So the last one was perfectly inelastic. When it's perfectly inelastic, they stick together. But when it's just inelastic, like this one, the objects will bounce off each other. But energy is still not conserved. Elastic is very similar to inelastic. They look exactly the same. The objects will bounce off each other and move separately. The difference here is that, remember, inelastic, we said kinetic energy is not conserved. But with elastic, kinetic energy is conserved. That means the object maintains its original shape. When two pool balls collide, most of the energy is conserved. So it's very difficult, if not impossible, to have an elastic collision in real life because there's always going to be some kind of sound when the objects collide. But we can say that the energy is conserved enough that it's considered elastic. So these examples could be inelastic, they could be elastic. You really have no idea just by looking at them because they look exactly the same. This is another fun video with pool trick shots.
I'm going to come back now. Are you going to do it? Yeah, I'm just coming right back here.
So those would all be considered inelastic or elastic. But when the balls fall into the pocket, that is perfectly inelastic. This is a perfectly inelastic collision because it lands in the cup. And again, that's perfectly inelastic. Okay. Well, we're not really concerned about this one. We do not deal with any glancing collisions. All of our other collisions we've looked at are considered head-on collisions. So I'm not going to go through these example problems right now. You're welcome to try them at a later time. I am going to have you write down some examples from a couple videos that I have made already. But hopefully you got down all the notes. If not, go back and make sure you have them all. Have a good day.